Welcome to another example of the inverse Laplace transform. So our job is to find the inverse Laplace transform of f of s equals negative 4s plus 7 over s cubed minus 4s squared plus 13s. So first thing we need to do is focus on the denominator, factor the denominator, get it into common forms. So focusing on the denominator, I guess I should read the problem. I apologize. We're looking at finding the inverse Laplace transform of f of s equals negative 4s plus 7 all over s cubed minus 4s squared plus 13s. So our denominator, we're looking at s cubed minus 4s squared plus 13s. We can go ahead and factor out an s. That leaves us with s squared minus 4s plus 13 inside. And then that s squared minus 4s plus 13, we can rewrite in standard complex root form. That would be an s minus 2 squared. That would be s squared minus 4s plus 4. Then we have a plus 3 squared remaining to complete our s squared minus 4s plus 13. So we essentially have factored our polynomial and gotten them into kind of standard form. So we have factored the denominator. And rewritten the quadratic factor. In s minus lambda squared plus omega squared form. That is our standard form for a denominator in our Laplace transform results. At this point, we are going to run partial fractions to break our original fraction. So from here, we should run partial fractions. So we have negative 4s plus 7 over s cubed minus 4s squared plus 13s. Should be what we're aiming for. So negative 4s plus 7. And our denominator is that s times s minus 2 squared plus 3 squared. On the left, we're going to have something over s plus something over s minus 2 squared plus 3 squared. The over s, we just have a constant. Since the denominator is linear factor, we're looking for just a constant up top. The second fraction is a quadratic denominator, so it needs a linear numerator. So it could be bs plus c. So again, if we have a quadratic denominator, our numerator should be a linear, just 1 degree lower. Continuing on from here, we can play our little trick of rewriting things. So this, we have that a times that s minus 2 squared plus 3 squared plus bs plus c times s should be equal to negative 4s plus 7. If we plug in s equals 0, that second component just goes to 0. So if we plug in s equals 0, then we have a times, we would have negative 2 squared is 4 plus 3 squared plus 9 becomes 8 times 13 plus 0 is equal to 7. And we therefore get that A should equal 7/13. At this point, we can kind of match coefficients if we want. So plugging in that matching coefficients. For x squared, or sorry, our s squared term, we would just have as squared plus bs squared should be equal to 0s squared. This tells us then that b should be equal to negative a. And so we get that b should be negative 7/13. And then we have a variety of methods we can use for the remaining one. Matching our s term, we have, we would have a negative 4as from that first term, and then a plus cs. Should be equal to that negative 4s on the right. And so we get that c minus 4a is the coefficient on the left, should be equal to negative 4. So c is equal to negative 4 plus 4a, or negative 4 plus 4 times 7/13. I apologize, I need to update my screen. So again, we had negative 4as plus cs. That coefficient was just c minus 4a. That should match the coefficient of negative 4 on the right. So we have c is equal to negative 4 plus 4a, or negative 4 plus 4 times 7/13. So we are looking at negative 52/13 plus 28/13, or negative 52 plus 28/13, which is negative 24/13. So going back to what we were starting with, we had a over s plus bs plus c over s minus 2 squared plus 3 squared. This was our f of s. So we have that f of s is equal to 7/13 times 1 over s, plus we have a negative 7/13 times s minus 24/13 all over s minus 2 squared plus 3 squared. Now that 1 over s is a form we're familiar with. The something over s minus 2 squared plus 3 squared. For this, we're looking for either s minus lambda over s minus lambda squared plus omega squared, or for omega over s minus lambda squared plus omega squared. Those are the two acceptable forms with the denominator we have. 1 over s is already in a form we're comfortable with. So this is in a form we know. So for this second one, our 2 is lambda. So we have lambda is 2 and omega is 3. So essentially what we need to do is we need to rewrite -7/13s minus 24/13 as a linear combination of those two possible forms. So again, what we need to do is we need to write -7/13s minus 24/13 as some number times s minus 2, there's our s minus lambda, plus some number e times omega, which in this case was 3. So I did d times s minus 2 plus e times 3. So in this case, matching coefficients, we immediately know that d must equal -7/13. And so, and then we get that -2d plus 3e must equal that -24/13. So we have -2 multiplying -7/13 plus 3e should equal our -24/13. We have 14/13 plus 3e equals -24/13. Or 3e is equal to -38/13. Or e is equal to -38/39. So we can rewrite our entire f of s now as f of s is equal to 7/13 times 1/s plus we have -7/13, so minus 7/13 times s minus 2 over s minus 2 squared plus 3 squared. And then we have minus 38/39 times 3 over s minus 2 squared plus 3 squared. So we've now split our original f of s into a series of, or a sum of a bunch of a linear combination of fractions, which we know the inverse Laplace transform for. 1/s is just the inverse, or is the Laplace transform of 1. So we have 7/13 times the Laplace transform of 1 minus 7/13 times the Laplace transform of s minus 2 over s minus 2 squared plus 3 squared. This is the Laplace transform of e to the lambda t times cosine omega t, where e to the lambda t is e to the 2t times cosine of 3t. Then we have minus 38/39 times the Laplace transform of 3 over s minus 2 squared plus 3 squared. That's our e to the lambda t sine of omega t. So we are looking at the Laplace transform of e to the 2t sine of 3t. This then gives us that the inverse Laplace transform of f of s should be equal to f of t, which is equal to 7/13 times 1 minus 7/13 times e to the 2t cosine of 3t minus 38/39 times e to the 2t sine of 3t. So this unit requires a fair amount of algebra, in particular, a good amount of partial fractions. So you will want to be familiar and comfortable with partial fractions in order to do most of these problems. In the next videos, we will look at why we take the Laplace transform and how we can use it to solve differential equations.